A7. The engine that put America in space. The A7 was a direct descendant of the German V2 rocket engine. It was a relatively simple single-start engine that burned liquid oxygen and a form of alcohol. As the power plant for the Redstone rocket, it was this engine that successfully launched America's first satellite, Explorer 1, and propelled its first astronauts, Alan Shepard and Gus Grissom, on their suborbital flights. It was the foundational engine of the American space program. Titan II engines. These were the engines that powered the Gemini program, the crucial bridge to the moon. The Gemini spacecraft was too heavy for the Redstone or Atlas rockets of the Mercury program, so NASA turned to the Air Force's powerful Titan II intercontinental ballistic missile. Its first stage was powered by a single LR-87 engine with 2 combustion chambers and nozzles, and its second stage used a single LR-91. NASA worked to man-rate these military engines, improving their reliability and safety for the 2-person Gemini crews who used their power to practice the rendezvous and docking essential for Apollo. H-1, the workhorse engine of the early Saturn program. The H-1 was an evolutionary step up from earlier engines, burning kerosene and liquid oxygen. It was designed to be reliable and built to be clustered. A powerful array of 8 H-1 engines powered the first stage of both the Saturn I and Saturn 1B rockets. These were the engines that powered the early uncrewed Apollo test flights, and most famously, launched all the crewed missions to the Skylab space station, making it the backbone of NASA's Earth-orbiting heavy lift capabilities. F-1, the most powerful single-chamber liquid-fueled rocket engine ever flown. The F-1 was a monstrous engine of brute force, designed with one purpose: to lift the colossal Saturn V moon rocket off the launch pad. 5 of these kerosene-burning engines were clustered on the rocket's first stage, together generating over 7.5 million pounds of thrust. The F-1 remains the benchmark for raw propulsive power and is an icon of the sheer scale of the Apollo program. J-2, the high-performance workhorse of the Apollo program. While the F-1 provided the brute force, the J-2 provided the high efficiency needed for the upper stages. Burning ultra-efficient liquid hydrogen, a cluster of 5 J-2 engines powered the second stage of the Saturn V. A single J-2 then powered the third stage, firing once to get into Earth orbit, and then, critically, reigniting in space to perform the trans-lunar injection burn that sent the Apollo astronauts on their way to the moon. Apollo SPS Engine. This was the interplanetary powerhouse of the Apollo spacecraft. A single, hyper-reliable engine on the back of the service module, the SPS was responsible for all major deep space maneuvers. It was the engine that fired to place the astronauts into lunar orbit and fired again to blast them out of orbit for the journey home. Famously, the Apollo 13 crisis showed how essential the SPS was to Apollo mission design, but after the explosion, the service module's SPS engine was considered unusable, and the crew's critical course correction burns were made with the lunar module's descent engine. Its ability to restart multiple times in deep space was essential to the entire lunar mission architecture. LM Descent Engine. One of the most unique and technically demanding engines ever built. This was the engine that landed humans on the moon. Housed in the lunar module's descent stage, it was the first rocket engine to successfully demonstrate deep 10-to-1 throttling on a crewed spaceflight mission, letting Neil Armstrong vary thrust to precisely control the lander's descent speed. This deep throttling capability was a crucial innovation that made a pinpoint landing possible. LM Ascent Engine, arguably the single most critical engine in human history. This was the small, simple engine on the lunar module's ascent stage. Its job was to fire once, without fail, to lift the astronauts off the lunar surface and get them back to the safety of the command module orbiting above. It was designed with extreme reliability as its only goal, because there was absolutely no backup. If this engine had failed, the astronauts would have been stranded on the moon forever. XLR-99, the power behind the hypersonic pioneers. The XLR-99 was not an orbital rocket engine, but the power plant for the X-15, one of NASA's most successful experimental programs. It was a remarkable engine for its time, fully throttleable and restartable, allowing X-15 pilots to control their thrust like a jet pilot. It was this powerful engine that propelled the X-15 to the very edge of space at speeds exceeding Mach 6, providing the foundational data on hypersonic flight and re-entry that was critical for the later Space Shuttle program. RL-10, the quiet, unsung hero of the upper stages. The RL-10 was the first practical rocket engine in the world to burn super-efficient liquid hydrogen and liquid oxygen. First flown in the 1960s on the Centaur upper stage, this highly reliable and efficient engine has been a workhorse for decades. It helped launch robotic explorers like Surveyor to the Moon and Voyager to the outer planets. Today, in a testament to its incredible design, modern versions of the RL-10 are still in use, powering the upper stage of the new Space Launch System rocket. Scout motors. This was not a single engine but a family of small, reliable, solid rocket motors that made up the 4 stages of the Scout launch vehicle. Motors like the Algol, Castor, and Antares were the backbone of NASA's small satellite workhorse for nearly 4 decades. Their simplicity and reliability as solid-fuel rockets meant the Scout could provide frequent and affordable access to orbit for dozens of scientific and technological satellites, making it a quiet but essential part of the NASA fleet. RS-25, the most sophisticated and efficient rocket engine ever built. The 3 RS-25s were the reusable, high-performance heart of the Space Shuttle. They were like the Formula One cars of rocket engines, incredibly complex, pushing the limits of temperature and pressure to achieve unparalleled efficiency. After each flight, they were removed, inspected, and refurbished for the next mission. In a testament to their incredible design, a fleet of proven, flight-tested RS-25 engines now serves as the expendable core stage engines for the new SLS moon rocket. Space Shuttle OMS engines. These were the on-orbit workhorses of the Space Shuttle. Separate from the powerful main engines used for ascent, the 2 orbital maneuvering system engines were located in pods on the shuttle's tail. These smaller, restartable engines were responsible for the final push into orbit after the main engines cut off, all orbital adjustments and rendezvous maneuvers, and the critical deorbit burn that started the journey back to Earth. J-2X, the engine that was meant to be the bridge between 2 eras of moon rockets. The J-2X was a modern, upgraded version of the legendary J-2 engine from the Apollo program. It was designed during the Constellation program to power the upper stages of the Ares 1 and Ares 5 rockets. It aimed to deliver higher performance and be more cost-effective than its predecessor. Though the Constellation program was canceled and the J-2X never flew, its development provided crucial data and expertise that informed the design of the upper stages for the modern Space Launch System. Orion Launch Abort System Motors. This is not a single engine, but a powerful system of 3 solid fuel motors designed for one purpose: to save the astronauts. Sitting atop the Orion capsule, the system includes a massive abort motor that fires with incredible force to pull the capsule away from an exploding rocket, an attitude control motor to steer the capsule, and a jettison motor to separate the tower once the emergency is over. It is the most powerful launch escape system ever designed, a direct lesson from the tragedies of the past. Commercial engines. While not designed by NASA, these SpaceX engines are now critical to its mission. The Merlin engine powers the Falcon 9 and Falcon Heavy rockets. For NASA, Falcon 9 has flown commercial crew and cargo missions, while Falcon Heavy has launched NASA science payloads. It is the engine behind Falcon 9's routine first-stage landing and reuse. The Raptor engine is the next-generation powerhouse for SpaceX's Starship, a revolutionary full-flow staged combustion engine burning methane. The Raptor is the engine that will power the Starship human landing system, making it the engine that will land the next NASA astronauts on the moon. Thanks for watching. Did I miss one you think deserves a spot? Let me know in the comments. Also, please remember to like and subscribe if you enjoyed this video.